All right, everyone. Welcome to Entrepreneurship Hour. We're glad to have you here. I'm Matt Gibson, the Director of Educational Programs at the Center for Entrepreneurship, and we have a great time ahead of us today. I'm thrilled. I would like to introduce our speaker today. Our guest is Gage. Gage is, in my view, one of the most interesting people in the world. He is the founder of an amazing company called Backyard Brains. He did his PhD research at the University of Michigan, where he studied neuroscience and neurotechnologies, but he was inspired to take that to the next level and really have an impact on the education, on science education, and to really help people try to understand neurological disorders and how we could actually have a big impact on how we address those things. Greg has taken a really interesting path to being an entrepreneur as well. So he took science, and he'll share with you how he applied his background in order to start a company. Among his many accomplishments, he is a senior fellow at TED, as in TED, those talks that you watch, not TEDx, but TED. He's been one of their featured speakers. His videos, his talks have been viewed by millions and millions of people, so we are grateful to have him here. He's won awards to the National Institutes of Health. He's been invited to the White House as a leader in citizen science, and he has a couple of kids and really enjoys changing their diapers, from what I hear. So with that, I'd like to welcome my good friend Greg Gage.
Matt also failed to mention that we were lab mates together for many, many years here at the University of Michigan. And so the talk today I told Matt before is called Local Boy Does Good. It's basically how we started the company in the Center for Entrepreneurship and sort of made it into a independence. I put an asterisk there, quasi-independence. We're all so close, but I think we're going to be there this year. So it's a bit of background story, and it's going to be maybe a different story than maybe you've heard in entrepreneurship. Most of the kind of things are going through kind of getting your slide together and pitching to venture capital and getting the funding to be able to do it. This is an alternative approach, which I think is also valid and interesting. And so, as I mentioned, I was working in a neuroscience lab with Matt, and we were lab mates together for many years. And my role was to understand, investigate the brain. So I'm a neuroscientist. What I like to do is understand how the brain works. How do the basically neurons in our brain allow us to do behaviors? And so we would be able to do that by having these really expensive rigs, that cost about $40,000 of U.S. taxpayer money, and we would have to work for about 6 to 7 years in a lab just to get access to these tools. So if you wanted to study the brain, you had to become a neuroscientist, and you had to dedicate your life, and you had to basically work for slave wages in a research institution like the University of Michigan. But that's a shame, because there's 1 out of 5 people, that's 20% of the entire world, has a neurological disorder. And how many cures do we have for neurological diseases? Guessing. 0, yeah, exactly 0. So, man, I had Alzheimer's the other day, but man, the doctors prescribed this pill, and now I'm better, You don't hear stuff like that because it doesn't exist. So we have 20% of the world with a neurological disorder, no known cures for these diseases yet. We're not teaching neuroscience until you've dedicated your life and become a neuroscientist, right? And so that's what we set out to do. It's not like this in other fields of science. For example, in astronomy, you don't have to get a PhD in astrophysics to begin to understand how the heavens move or start to make some recordings of stars and planet positions. And in fact, many amateurs are contributing significantly to the field. So the Hale-Bopp comet was discovered by an amateur. Many exoplanets are being discovered by amateurs. So not only are they getting interested, but they're also making serious contributions to the field. So it's not like that in the biological sciences. You have to get a PhD to do a lot of these experiments. And there's almost 0 amateurs actually contribute to the fields. We want to change that. And so around this time, we were thinking, well, what can we do? Obama just got elected. Be the change you want to be in the world, right? So we went out to schools, and we were teaching about our research, and we would put up here is a paper mache Frankenstein, where we had an ice cream brain in it, and we would scoop out a part of the brain and we would transfer that lesion to another student. So if you took out the motor cortex, the transmodulator would take it out of the student, and then the student wouldn't be able to move its hands, right? And so then, same thing, visual cortex. But the kind of the joke was, inside of this was the actual person, but the students didn't. We made it look like there wasn't like gloves and like paper. And the last part of the brain was the amygdala. Does anyone know what the amygdala does? It's the fear center. And so then like, oh no, you took out the amygdala. And then the guy would stand up, and then all the kids would run out. And so it was kind of fun. So, and what we found is that by doing this, kids were learning the different parts of the brain do different things, but it wasn't quite getting at the cool stuff that I was doing in the lab with Tim, my co-founder. And what we decided is that we needed to come up with a way to make what we do in the lab become something that the students can do. So understanding how the brain works at the physical level and bringing that into a fifth grade classroom, can that be done? So we set about on a self-imposed engineering challenge. We called it the $100 Spike. And as good scientists, we published it in the Society for Neuroscience as an annual conference. It's the largest, about 30 to 40,000 neuroscientists show up in one spot at one time. It's very nice. And so in the abstract, we wrote, we're going to try to record a spike, which is what a neuron communicates with, for less than $100. Stop by our poster and see how we do. And then, so you submit the abstract in March, and we had all summer long to work on that. And then the fall, we showed up with our poster, which is actually a 3D poster, because we actually had a table, and we brought our prototypes. So you could see we've got some, balsa wood and wing nuts, kind of holding some. This is laboratory equipment that we're beginning to develop. And so here's our circuit here, and this is Tim, my lab mate at the time, and that's me. And so what we showed was that there is the idea that this could be done. So we showed that you can record a spike for less than $100. And we started to get picked up. So the journal Nature did a story about this. And then we got on the Neuropod, the Nature podcast. And then we started getting these emails all the time about, hey, this $100 spike thing you're doing is pretty cool. Can I buy one of those? And then other people saying, you're doing such a great job, keep pushing it forward. It's extremely important to do what you're doing. And then in my day job, I was publishing, which I thought were kind of these glamour papers, like in Neuron, these beautiful papers, investigating fast-bunking inner neurons. But I never got one email saying, hey man, that FSI paper you did where you found the action selection really peaked the firing it's so important, and so thank you for doing that. Not one of those emails, but this other side project, I'm getting, maybe 25 emails a week. And slowly, and it's funny because what I was researching was how does the brain adopt behaviors based upon the basal ganglia, which has the dopamine systems. And so I'm getting these positive rewards on the side project and kind of nothing on my main project. And slowly, in graduate school, I realized that maybe the side project should be the real project. And so also at that time, there was a big problem that was happening in academics, and it's still happening even worse today, and that is we are generating way too many PhDs for the amount of academic positions that are available. And so it's almost like a Ponzi scheme that every grad has 1 to 7 graduate students, and the only way to get a faculty position is somebody dies, or if a school expands. And so there's not many expansion going on anymore. There was for a period in the early 2000s. So anyway, so what is happening is that people are sort of doing postdoc after postdoc after postdoc, and you end up, what used to be 1 postdoc now turned into 2, turned into 3, and now you have these career kind of people that are just kind of in somebody's lab, which is not really, if you want to be an independent scientist, it's not as fun. So we decided instead to go down the entrepreneurial route. So this is Tim and I doing the Dare to Dream program. Is that program still around? Has anyone even heard of this program? So it was a partnership between kind of the engineering school and the business school. And there were small grants, maybe like $500, but we won it. So we pitched our idea, like, we found out that people need this. We'd like to build it. So we won. This is our we called it $100 Spike at the time. And then we got hooked up with the Center for Entrepreneurship, and we won a pitch contest and got to go to pitch our stuff all the way out in California. These are a panel of VC and business people that we pitched our idea. We want to make this neuroscience gear available for K through 12 and for general public. What do you guys think? And they're like, nah, like thumbs down, the worst idea ever, right? So then we kind of cold walked into Y Combinator, and we were pitching the idea to those guys, and Paul's like, no, I mean, good idea, guys, good on you, but that's not a good idea. All right, so it's all right. So we keep getting rejected because the reason why is that it's a cool idea that people think it's great, but there's no market there. There's no demand for neuroscience gear in K through 12. And so we had to create the demand first, which is a hard thing to sell to kind of VC capital. So we did come back to the University of Michigan, and we started in TechArb, and that's still around, I think. But this is back when it was in a cooler spot. So this is you guys ever go through that alley in downtown Ann Arbor where you see all that graffiti? That's where the TechArb used to be. There's a side door right here, which I cut out. It was in the basement, and so this is our very first office, and we were setting it up there. We were sort of starting to launch this idea. We made a website, doing what all good companies should do. And we got on, this is Thomas DeBrook, and he used to head up the CFE. He's now at NASA. But we started getting some popular press. This is the PBS came to town. That's Ray Suarez, and we got on TV our first time. We thought it was super cool. We're like, all right, maybe we're onto something, you know. But still, we had some challenges along the way. But we started this company called Backyard Brains, and we sort of even outgrew the small space there. Because one thing, it may have changed now, but TechArb was very different. It was really kind of geared kind of for the software-based companies, or kind of like intellectual companies, not people that are kind of doing honest work, I call it. So this is my kitchen room table. So we would set up an electronics bench there, and I had the mass production was being done there. This is Tim cutting some wood. So we made all of our enclosures out of wood for the first about 100 boards that we sold. And so, yeah, it wasn't a very clean way to sort of keep your house in order, but it was a way that we could expand and actually start taking the money that we got from these Dare to Dream grants. We would buy the components and we would start selling them. And so we still had day jobs. I was in grad school. Tim was, I think, a postdoc by that time. But we were starting to have, we opened up a bank account and we were starting to collect money. So we were starting to, we even paid ourselves a few times from that. So it was an exciting time as we started. And then the money started really coming in when we did a Startup Chile. It's an entrepreneurship program down in South America. And so we got $40,000 there. Now we could start. I could quit my job I finished my PhD in 2010, but I was still kind of working part time as a postdoc, and I went from like 50% down to 20% down to nothing when we got this guy. So we were down to South America, and we started to build up the program down there. And so, about maybe a year later, we actually had full-time employees. We had people working in Ann Arbor. So I came back to Ann Arbor in 2012. But even before then, we had full-time people based here. We were still based in Ann Arbor, down in a makerspace underneath the Michigan Theater at the time, called All Hands Active. But we could then go out to conferences and start to pitch our ideas to people and get people interested in this. This is at Society for Neuroscience. We went to the National Science Teachers Association. But anyway, so we're starting to take off. And then we wrote a grant to the NIH, and that got funded, which that changed everything. So now this Small Business Innovative Research Program takes ideas that are not quite ready for prime time, but are innovative and they're research-based, and they'll dump a lot of money in that. So we finally got some government funding to help us out, which is cool. So this is where we started. So when we were presenting our poster at Society for Neuroscience, it started here, and our invention got smaller and smaller. We realized it got too small, so we made it a little bit bigger, so that we can actually do some stuff with our press. But I've been talking a lot kind of about the business side, but let me talk about a bit on the biological side, because this is the invention right here that we came up with back at that poster, and we call it the Spiker Box. And it replaces about $40,000 worth of lab equipment, and you can do it with your own computer. So you basically use your tablet or your iPhone to be able to actually see how the brain activity works. You guys with me so far? All right. So I'm going to show you where we are today. So just to give you an idea. So this is when we started. I was still in grad school in 2006. We started selling it when I was in grad. I think I graduated right around here. But we actually started making our websites. Our sales started slowly increasing, and then so here we are today. And our burn rate, I put it on here for last year, it was about $72,000. And so there's a gap here, right, between what we're taking in. There's our monthly revenue. And this is our monthly, kind of our average monthly expenditure. So the gaps right here are kind of made up by grant funding. So that's where we get the SBIR funding for, and especially here in the beginning where we had a lot of, actually our burn rate was much lower, but actually our burn rate dropped from 2015 to 2016 even though our sales went up, which is kind of cool. So we're getting a little bit more efficient as well. All right, but I want to get back into the neuroscience of it. I am a neuroscientist, and I want to do a couple of quick demos to kind of demonstrate how the brain works. And I need some volunteers, but I won't get to that in a second. I'll back up and describe the brain. So if Matt Gibson was up here, he'd be able to nail this, but I'll try to do this as best as I can, Matt. So this is a cell. Does everyone know this is the cell body? What is this right here? This is mitochondria. What's this? Nucleus. What's this? No, I don't know. That's the artist, just your little thing. Organelle. But the important thing I want to get at is this guy right here. Anyone know what this guy is called? It's a special, we call these processes. Processes are things that leave the center body. So these are processes in the back. It's a process. It's a this whole thing is a neuron. And what's this part right here called? Axon. All right, you guys are good. All right, some of y'all. So I had to go to grad school to learn that word. I didn't even know that before. So the axons kind of reach out and they touch other cells. They don't quite touch them. They get really close to them, and they send messages. This is how our brain sees things. And so the message is made out of electricity. Why is it electrical? Does anyone know why the brain uses electricity? Because what? Fast. Yeah. So most of the messaging in our body is chemical, but they're slow. I'm slow. I'm getting hungry. You know, you slowly comes out, right? But if you're gonna be hit by a car, you don't be like, oh, you know, like this. It's like a fart. It's like super slow to sense it, right? So you don't want to have that to be the way to jump out of a car. So it uses electricity, which is extremely fast, and we can actually measure how fast it is in our laboratory. But the most important thing is that the electricity comes in a very unique packet. It's like the euro, the common currency of the brain. It's which your vision, you see me, you hear me, you can understand what I'm saying. You have a percept of who I am as a person. All this is being encoded by these little spikes right here that are coming in from your eyeball back to your visual cortex or for your ears back in. And it creates a thing called consciousness, which we don't understand as neuroscientists how it works yet. But then it comes out to your motor cortex. Same spikes are going out to your body and moving your bodies around. So it's like inputs, consciousness, and outputs are the three things that the brain does. And they're all driven by these guys right here, these spikes. And so what we're going to try to do today is try to record these spikes right here. And to do so, I'm going to need a volunteer from the audience. Document camera. All right. So what I have for you, Corey, I've got this in here. I want you to take a look in there and get comfortable with that. Because what we're going to do now, what's in there? Yeah, gigantic South American cockroaches. So you can put it on here so everyone can see it. All right. All right, can y'all see that? All right, so, we cool? Yeah, I'm giving you a mic. Oh, okay, gotcha. I got a hand on mic. All right, so these guys, they come from South America. They kind of live in the barks of trees. All right. And so I'm going to have you, Corey, you're going to be our anesthesiologist. All right. So you seem to be a little bit taken back by that. So I want to just do really quickly, I like at this point to do a PSA on behalf of the poor cockroach. Yeah, so obviously you weren't in Mary Markley dorm room, because they're like a roach. So this is people that have forever hated roaches, but why? They're insects, right? There are other insects we like. We all love dragonflies and ladybugs and butterflies. If this was a ladybug, you'd be like, oh, you'd be putting it on you, you'd let it dance around, and then you let it fly away. But it's it's a cousin of those guys. But these guys are la cucarachas. You can hold the box. They're la cucarachas, and what I'm here to tell you is that these cockroaches are very, very similar to us as far as their nervous systems are concerned. So the human brain is made up of how many neurons are in the human brain? Does anyone know? It's a facts. Close, yeah. I used to say 100 million, and then someone in the audience says, I actually published a paper, we counted it, it's 80 billion. So it's 80 billion neurons. Did you say million or billion? Billion. Okay, yeah. So it's roughly about 100 billion neurons, right on. So, but I've been corrected, 80 billion neurons inside the human brain. How many are in the cockroach brain, do you think? 5 neurons, more than 5. It's about 1 million. But if you took a slice of brain tissue, stained it, took it under a microscope, and you had one labeled A and one labeled B, and you told me one of these is a human, I wouldn't be able to tell the difference because the size of the cells are the same, all right? And even the organ, how are you doing there? You all right? Okay, so even the organism layout is the same. So about 500 million years ago, or 500 million years ago, the nervous system evolved, and we think it only evolved once. And so you can even see in the cockroach, there's kind of a brain structure, and they call it the ventral nerve cord. It's on the front side, but we have a spinal cord in the back, which together makes the central nervous system. But these are very, very similar. The neurons have the exact same electrical spikes that we do. So by using this cockroach, how are you doing there? You all right? All right, you're still getting there. All right. So I'll give you some time to kind of get used to the cockroach. But what we're going to do now is we're going to reproduce an experiment that was first done in 1927, and this was done by Sir Lord Adrian, and he was very surprised to hear the spikes for the very first time. So electronics was just starting to come on the scene. They had this bioamplifier, and he was trying to do something else, and he heard these spikes. So we're going to do that right now, but we need to anesthetize the cockroach. That's why you're up here. All right. So are you ready?
All right.
So your job now is we're going to anesthetize this cockroach, okay?
Okay.
And so we're going to do that. You are our anesthesiologist, and we're going to do that by taking some ice water here. I'm going to take some ice. I'm actually going to use my espresso cup here. I'll switch back over to projector control and volume. This thing is so Hollywood. All right, document camera. Okay. So now, I'll move this one over here. So I've got a little cup here. And we're going to add some ice to this. Okay. And we're going to add some water to that ice. And this becomes ice water. Right? Science. All right. So, all right. So now what we need to do, this actually might be too small. I'm going to put some ice in here, water in here. Maybe we'll use the big one. Yeah, this would be better. That way we can't escape. All right. All right, so Corey, what I need you to do, I need you to take a cockroach out and stick him inside the ice water.
Do you have like a glove or like?
No, our protocol does not require gloves. The E-hour, by agreeing to sign up for the E-hour course, you have given away your rights as a human. All right, so come here. You can just knock him. I'll take him out like this. I'll try to take a few off.
Yeah, do it.
All right. Okay, I'll take it off here. Okay, here you go, perfect. All right, so Corey, hey, come back. So all you have to do, I don't want to touch these guys. So you can use this stick. You can hold it this way. Do you want to call in a lifeline? All right. You can knock him in the ice water. And I want you to notice. There you go. There you go, fear factor. There you go. You got it. Don't poke his eyes. All right, you got it. All right, so now he's in there. So now you got to dunk him in. I'll put these ones back. Just gently, but don't poke him. Here, turn it around this way. So turn it around this way. So now poke him in that way. All right. I don't want you to jam him in the back. All right. Good. All right. So one more time. Just put him under the ice. Okay. All right. There we go. All right. Oopsie, woo. All right. All right, so I called you our anesthesiologist. So does anyone know what an anesthesiologist does? What does an anesthesiologist do?
Doesn't it put something to sleep?
Yeah, so it's the most, it's a very important job. So it's to anesthetize somebody, right? And so they get paid a lot of money for doing a little bit of work. But I was told once, someone says, my mom's an anesthesiologist. I'm like, oh, sorry about that. But he said that the reason why they get paid a lot is because it's not to knock them out, right? Anyone could knock anyone else, but it's waking them back up is the most important thing, right? So it's a reversible process. And so what we're doing right now, we put the cockroach inside the ice water. And what's one of the major differences between a cockroach and a human, or insects and humans? About our blood type. Like we are.
Aren't we like warm blooded?
Warm blooded, right? So these guys are cold blooded. So right now he's becoming the same temperature as the ice water.
Right.
And So inside of his body, it's the same as the outside. And therefore, what's happening on the inside? So you can look right here. There's a behavioral change in this guy. So is he still alive, do you think?
Probably it's sleep.
Yeah, so he's asleep. And so the nice thing is, so if you remember, I didn't go into it, but those spikes that are occurring are happening because ion channels open and close. Right. And when things get colder, what happens? They slow down. When things slow down, the kinematics change, and the ion channels, they can't open and close. They can't fire spikes. And when you can't fire spikes, you can't move anymore. Right. And if you can't move anymore, you can't feel pain. So that's the reason why we call you the anesthesiologist. You knock them out. So please give a big round of applause for Corey for helping us out here. All right. So now we need to do one more thing. I'm going to need another volunteer from the audience to be a neurosurgeon. So what we need to do, I want to record from the neurons that are inside of his leg. So if you look here, these have got these beautiful hairs all up and down the leg right there, right? And in each one of those hairs, there's a cell here. What cell is this? Neuron, all right? That talks about neurons. Okay, there's a neuron here. And what's this coming out of the leg? The axon, all right. So the job of this neuron is to detect little vibrations, right? So if you're walking into your room, you turn on the lights, and all of a sudden you think skittering away. Well, they've already felt you coming, which is why it creeps people out, is that they are the fastest body length to speed ratio, right? So they can move extremely fast. If you blew up a cockroach the size of a cheetah, it would be faster. So they're kind of creepy. But they get a head start because they can sense you coming. So what we want to do is we want to cut off the leg and warm it back up again so that we can get those neurons to fire, all right? So that's where you come in. We're going to do one more PSA, and this is on behalf of the cockroach. So this is a paper we published just last year. This is the leg that was cut off, and this is the leg that was normal. And you notice after 45 days what happens. You see it's a little nub of a leg, right? Isn't that cool? So then if you wait about another 40 days, you get to see it's 123 days later. Look at this guy. So can you tell which leg was cut off and which one was not? So what does that mean? The cockroach have ability to regrow their legs. And so this is an escape response. So when a cockroach gets bitten by something, he just rips his leg off and runs off. And they can run just as fast with 5 legs as with 6. They also regrow their antennas, a bunch of cool things that cockroaches can do. All right. So now what we're going to do is we want to warm up that leg. So I'm going to put the document camera back on. Peyton is going to help us out here. So this is our surgery table. Our sterile, any biomedical engineers here? This is our sterile field. All right. Why is it? There we go. That looks normal. All right. So now I'm going to take this guy out, and I want you to cut off. It's really hard to see here. Let's see if I can rotate. There's a light on there, and as I can zoom in, zoom. Here we go. Let's get in there. And I'm going to use this piece of paper so we can get a good contrast. Oh, there we go. Now we're cooking with gas. All right. There we go. Let me zoom in a little bit more so we can see what Peyton sees. All right. It's still kind of hard, but all right. But you guys can see the hairs on his leg right here, these kind of hairs right here. So those are the neurons we're going to record from. But what I'm going to do, I'm going to hold up his leg slightly, and I want you to kind of go in there and kind of closer to the body than you are right now. Yeah, kind of like, not too close, but yeah, kind of right around there. Yeah, right around the knee. You can cut it right there. Perfect. All right. So Peyton, look at that. That's beautiful. All right. So now you need to put it in your hands and kind of warm it up a little bit. All right. So here, put your hand out. And we'll keep it in there. Oh, your hands are nice and warm. Okay. So while he's doing that, can everyone see those hairs? So inside those hairs, remember, oh, it's really dark. Okay, but doesn't matter. Inside those hairs, there's neurons. Those neurons are sending information up to the brain. But even though the brain isn't there, these neurons are still going to be alive. If I cut off your arm, how long would your arm last? Maybe 2 minutes, and then it starts turning gangrene, stinking, right? So these guys are different because they can breathe through their skin. The other cool thing about invertebrates is they breathe through their skin. They have called spiracles all up and down their bodies, which allow it to change oxygen for carbon dioxide. So these neurons are still alive, and so now that he's warming them up, Peyton's got them all firing again. They don't know they're disconnected, so they're going to keep sending information to the brain, even though the brain is sitting in that thing right there. Has everyone with us so far? So this is a living leg with living neurons on it. So now what we need to do is have an electrophysiologist. So Peyton, if you could lay that one down, and we'll get one more volunteer to be our electrophysiologist, and we'll take a look at this beautiful thing while we're waiting. So there we go. So now what we're going to do is the electrophysiologist is the person who's going to put the electrodes inside the cockroach leg to understand how the brain works. All right, so you're going to record the electrical activity using the metal pins that are on there. So if you were in a hospital and you had like, if I had like seizures that didn't respond to medication, I would talk to you. What is your name? McCoy. Like, hey, McCoy, man, I'm having these seizures and I can't stop them. You're like, all right, no worries. I'm going to talk to Peyton. He's going to come over. He's going to open up your brain. And then I'm going to put some electrodes on your brain, and I'm going to wait for you to have a seizure again. And I'll sit there, I'm reading the paper for a day and a half, and then I have another seizure. And then when I do, you get excited. You come into the room, and you read all the readouts on the computer, and you find out where the center of that seizure is, and you call Peyton. He comes in and cuts my, my part of that brain out. And then this is literally the treatment for incurable seizures. And it requires recording the electrical activity from the surface of the brain to understand what the neural activity is happening on the inside, okay? So that's what you're going to do over here. So I put it back onto the document camera. And we're going to put the electrodes inside this cockroach leg in 2 different locations. And so I'll let you choose where, but it doesn't really matter where. But you can just, let me zoom out a little bit. Yeah, so you can put one there, maybe. Yeah, it's going to be crunchy, but you can push it. We have a cork board that's right on there. You can go all the way through the leg into the cork, so it's going to be able to be in situ, in place. It's a Latin term that we use in science. All right, perfect. And then, yeah, another one right there. So why do we need 2 connectors? So these are metal pins, metal conduct electricity. Why do we need 2 pins? Yeah, you're connected voltage difference, right? So it's always A minus B type of thing. So we're going to take the difference between the 2 pins in the legs. We have one leg here. I'll have you stay up here for a second. Oh, sweet. One pin through the leg here and one pin through the leg here. All right. And so I'm going to, is that a pin through the leg? We'll find out. So we'll do an experiment. All right. All right. So I'm going to go ahead and we're going to turn, I have a little Radio Shack speaker, you know. Rest in peace. All right. And it's funny because this company wouldn't have started without Radio Shack. So it's a shame to see what's happening. And they missed it. They missed it by, I mean, like the maker revolution is happening, and now people need Radio Shack. All right. So I'm going to go ahead and have you turn this on, and we can listen to what's happening inside the brain. Yeah. Interesting. All right. I'm going to have it. Where's that microphone? Yeah, Christine took it. Okay. Actually, I can just, all right, we'll do this one. So we're going to listen to now what it sounds like possibly if I put these electrodes into your brain, all right? What does that sound like? Static, noise. Okay, yeah. Is it working? Do you think it's working? All right, so do you guys hear any patterns in here? Maybe it's hard to hear. Can you guys hear this? I can hear it.
It's like a bump up and down.
Yeah, it sounds like maybe raindrops. Or maybe you can close your eyes and just listen. Imagine you're in a campground at night, you know, in your sleeping bag. So it sounds like raindrops to me. That's why I say that. When people say it sounds like popcorn or maybe it sounds like sizzling bacon or something like that. But to me, that sounds like rain. And actually, the raindrop, if you hold this for a second, I'll actually put it right here. This setup is so cool. So we can actually look at what those raindrops look like, and I'm going to argue that what we're listening to is actual brain activity, and these are the spikes. Okay, so I'm going to open up my iPad here. Oopsie. And right now it's picking up my voice, but if I plug in this guy here, it turns off the internal microphone, and it uses whatever's on this guy here. And so if you want to plug that green one into there. All right, now we're talking. So I'm gonna see if I can put it up on the screen here. Let's actually let me zoom out a little bit more. It's kind of hard to see. It's going by pretty quickly. So what we're gonna do, I'm gonna put a threshold. So we're just gonna stop the voltage if it goes up a certain point, so we can see it. Okay. Always eat your own dog food. This is a beta version. I'll just put it on 1 for right now. So I'm gonna lower it down a little bit. So every once in a while, you see that little voltage that comes by, and it's paused there for a second. This is 50 milliseconds roughly. And the spike width is about 1 millisecond. This is 1 millisecond. We can average it a few times. This is a trick that you use as electrophysiologist that makes your spikes look better. So now if I zoom in on it, what does that look like? It's a textbook example. I should probably hold it this way so you guys can see it. This is a textbook example of what a spike looks like. This is sodium, potassium, all happening inside this cockroach leg that allows it to kind of create this shape. This is kind of cool. So this is, again, when you see me right now, see all these spikes are coming by, this is information being coded. You have this in your brain when it's like in the movie The Matrix when you said, oh my God, that's reality. This is reality. This is really what's happening inside of you. But we want to do an experiment. We are experimentalists, right? So let's do an experiment. So is it Marco? McCoy. Yeah. McCoy is going to touch the leg, and we're going to see, I'm going to block it so you can't see when he's touching it, but we're going to see if we can tell. We guys are all the central nervous system now. So everyone can see that, right? So go ahead and try touching the hairs close to the edge. Ooh. So there's something, that's kind of cool. So you're starting to see a change in the electrical activity, okay? All right, that was me touching this thing here. All right, do it one more time. It's like cool. You guys know what that was? Your pin came out in the back. All right, so every experiment needs a control. All right, but so you guys get the idea. So thank you so much. Yeah. You can have a seat, McCoy. All right, I'll move on beyond that. And so what we were able to do, we were able to record spikes. So this is how the brain encodes information. And we'll just go over it really briefly here and explain. So this is, so I don't know if you may have noticed, you heard that, that's one neuron repeating itself multiple times. And it sounds like, sometimes it gets like up to about, anywhere up to I think it's 500 hertz is the fastest neuron. But anyway, it gets up to easily hundreds of hertz. So here is two different neurons. So remember, the pin is just stuck to the leg. Axons are flying by. Some are closer than others, so some will appear bigger, and some are a bit smaller. But the axons are always the same shape. That was what that one we looked at. So this is the spike right here. Remember that shape that we looked at? And so here's when you touch the leg, the little hairs on the leg, you get an increase in the number of spikes per second, but not an increase in the size or the shape. So the shapes are the same, but the rate is encoding. We call this rate coding as a neuroscientist. It takes a long time to figure this out. But this is how, so we know pretty well how the inputs of the brain get encoded. We know how the outputs of the brain get encoded, but we don't quite know that consciousness step is in the middle. So why is this important? So we have also published a bunch of papers on these to sort of explain to people how to do this in their institutional setting. So here is another experiment. I'm not sure if we can get sound on this, but I'll try it. Yeah, here we go, cool. So now I'm placing an electrode into the neck of the grasshopper here. And so when I move a stylus, those are those spikes again. You can hear the spikes increasing. So what do you think those spikes are encoding? Is it the wind? So if I move it really slowly, so what else could it be? Remember, if it's in the neck. So we're going to do an experiment now and try to explore why would they have visual cues inside the neck. And so we're going to throw an object at it pretty quickly. Are you guys ready? All right, so there it is. So you guys see a response inside the neck of a looming object. So we're going to do it again. Notice when the spikes fire versus when it gets hit. Does anyone notice what's happening? So before the poor grasshopper gets hit by a virtual object, the neurons inside the brain is decoding something's coming towards it, sends a signal down the neck to do what? To jump. This is an escape response. So this is cool. So this is a paper we just submitted yesterday to publish. But this is, so here if you throw the object slowly, he gets plenty of notice to escape. If you throw it a little bit faster, he gets a little bit less notice, but he can still escape. But if you throw it fast enough, you can actually catch the poor grasshopper, right? So this is how we can actually determine how fast you have to be to actually catch a grasshopper. And what's cool about this is our data from 2017, and this is a paper that was published in Science, one of the top science journals in the world. And I should probably put on the same time scale, but this is showing you the same data set that we can generate. So now there's no difference. You don't have to be in a graduate level research student. You can just use, this is all made on the iPad, being recorded from a $50 amp kit, and you're able to sort of collect data to publish in the one of the highest prestigious magazines, one of the glam mags in the world. All right, so we also, when we started the company, we had this idea of a kind of DIY, so we give away the schematics for it and the parts list. And one of the things that was kind of near and dear to us is we wanted it to be a learning experience. And so for every resistor and capacitor, we would tell you not only what the values are, but why we chose it. What were the laws of man or the laws of nature that allowed us to choose R7 as like a 20K resistor. I'm not going to do it now, but we can do some fun stuff with the cockroach leg. We can hook it up and reproduce an experiment that was done in the 1750s by Luigi Galvani, which is like, he did stuff with frog legs. But if I play hip hop music into a cockroach leg, if I just hooked it up to my iPhone, you would be able to see the cockroach leg come to life again. So it would start moving again because of the current that's inside the iPhone is the same as the current inside of our brain. So we use electrons that pass through. It goes into the cockroach leg and turns into the sodium and ion potassium. They all have charges to them, and it flows through the cell, causes that cell to fire a spike and get to move again. Why is this cool, other than the fact you can see the cockroach leg moving, is that you're actually, by doing some very careful experiments in the classroom, you can actually determine that the peak frequency of firing is right around 100 hertz. And if you went to the literature and you started looking at how does deep brain stimulation, like what frequencies are they firing at, or cochlear implants, it turns out that they're using the same frequency. So it's a learning experience to sort of show off something that we do in neuroscience. So I did want to show one video of this. So this is we do work in Woods Hole, the marine biological labs, every summer, and we get to work on some cool preps. This is my favorite one. This is the squid that comes right off the shore of near Boston. And so if you suck in the nerve into an electrode holder here, and I put the other end of the electrode into my phone, and I'm going to show you the results of this. So squids are cephalopods. Cephalopods are the only animals that can control the color of their skin by their brains. And so what we're going to do is look at what happens when you play hip-hop music into the squid brain, all right?
Were you trying to get crazy with this?
This is through a microscope. These are cells. All right, this is cool. So you're seeing when the bass frequency particularly hits the cells, it causes a spike. The spike innervates a ring of muscles around each chromatophore and exposes the pigmented skin. So there's brown, there's pink, and there's yellow segments in there. So it's kind of cool. It's a pretty compelling way to show that it's a pretty compelling way to show that the electrical activity from your cell phones are the same as the electrical activity inside your brain. All right. I'm going to briefly mention this one. This is our project that we started here. It's near and dear to our hearts because it came out of a lab that was here at the University of Michigan in the basement where Matt and I were studying. They did a cyborg. We wanted to do one too. It shouldn't be just the scientists that have millions of DARPA funding to be able to do a cyborg. So we created our own version, a DIY version of a robot cyborg to sort of show students how do you get cochlear implants to work. For example, microstimulation into the nervous system to make a perception of something that's not there because we're lacking the type of perceptions that are there. So anyway, I'm going to explain briefly how it works. So the cockroaches have antennas. The antennas have hairs. We already saw from our other experiment that the cells inside of the hairs are sending information back to the brain. And then, so we can touch the cockroach on the side, and the cockroach is going to turn if you touch the hair. So if we can send a wire into the brain and cause it to fire, we can get the cockroach to turn using our Bluetooth backpack here. And if we connect to it, I'll show you a quick video how this works, and then we'll wrap it up. So I'm going to connect to the cockroach. All right. And so if I touch virtually on his antenna here, the cockroach thinks he's touching us. I'm sending the signal across to his neurons at that 100 hertz frequency. And now you can take your cockroach out for a walk. All right. There we go. So he's in the back, he's to the right. So we now know how this works because the neurons are inside his antenna are sending information to his brain is decoding that. He thinks it's a natural stimuli, so he's going to respond to it. But even though there's nothing there, so it's kind of cool. So this is a cool way to sort of show the technology and how it works. All right. So I think with that, am I out of time? I think I'm out of time. We're done. All right. 2 minutes. Let's do one more experiment. We're going to do one. I need a quick volunteer to come forward. All right. You come on down, right behind there. Okay. Take your jacket off. All right. I'm going to record now from your brain through your motor cortex. All right, we're going to do a bunch of cool stuff. All right. So what we're going to do is I'm going to record from the cells right here. So if you turn your body this way, if you have on this side, your motor cortex fires an action potential. It synapses on your spinal cord. It comes out here. So if I quickly put electrodes on here and here, we're going to capture the electrical activity that's coming from the motor cortex out to your body and be able to hear it and maybe do something cool with it. All right, so we're going to end it on that. Okay, so I'm going to put the electrodes. Here's our new invention. So we come about 2 inventions a year. And so this is going to record the motor output from the motor units inside your upper motor neuron, inside the motor cortex, and your lower motor unit, which is inside your spinal cord. As it innervates your body, we're going to hear. All right, so when you're ready, I want you to squeeze your hand. All right, relax and pump it a few times like this. Okay, so now we're going to do, so what's cool, let's walk over here now. We're going to use the maker revolution. Yeah, it's like a leash. I take him out for a walk. And you guys are not going to think this is cool, but this is the hello world in physical computing. So the first thing we're going to do is now we can record that electrical activity. So now I put it into an Arduino shield. Arduino is a little mini computer. You can make it do stuff. So you just squeeze your hand. So go ahead. Yeah. So now we can get it's like a little love meter, right? So it's like your cold fish, red hot lovers. All right. So this is a way. It sounds very simple, but this is a way that his brain is being picked up by his EMG, electromyograms here, being sent into the computer. Now you can control things by moving your muscles, by your brain. Your motor cortex is connected to this computer. So go do it again. And now what we're going to do is I'm going to take and make it a little bit more interesting, and we're going to add a robotic element to that. So I'm going to have you hold this in your hand here. All right, and we're going to plug this into here. So now when you squeeze your hand, so this is now a brain-machine interface. This is funny. The lab that Matt and I were in was the neural engineering lab. This is what we did all day. So this is a kind of a DIY way with an open source microcontroller called the Arduino with the open source shield that we made and a couple of laser cutter and a few other just creative ideas. You can make something that's kind of cool. It's a brain-machine interface. So I think with that, I've run out of time, but I'll open the floor up for a few, maybe 1 or 2 questions, and I'll call it a day. Thank you guys so much for being patient. Cheers.
When can I buy this?
Yeah, so we have, this is the reason why our sales are so low. We're not really good at marketing and sales, but we are good at being engineers and scientists. We sell them online through Backyard Brains. We now have we have 2 distributors that we're starting to work with this year to actually get our stuff into school catalogs. And so, yeah, we're based right downtown Ann Arbor above kind of Get Your Game On and See Eyewear. You guys know where that is, by Starbucks on State Street. And so we have a large office there, and we have all of our stuff is designed and engineered right here in Ann Arbor. And we also still have a lab at the Makerspace. So feel free, if you see Backyard Brains on the window, you can stop by and come on up and say, hey man, I saw you give your spiel at CFE. It was cool. So I appreciate that.
All right, with that, thank you, Greg.
Thank you.
Team has business, law, engineering, and athletic experience, and we're looking for mentorship to help us bring these products to market. Thank you.
Excellent. All right. So for the first time today, we have 2 mentors who turned around.